Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Glennys Farrar with us today. Hello, Glennys.
Hi there, Frank. It's terrific to be here.
Well, thanks for agreeing to talk about your very awesome article, which we'll get to here in a little bit. Let's see. And Glennys, well, let's ask it this way. What is your current geolocation?
I'm in Phoenix, Arizona, not that far from you.
Yes, and I hope you're enjoying the lovely
Oh,
December
wow,
weather that
am
we get.
I?
Very nice. And what is your usual geolocation, or what's your home institution? Let's
New
put it
York City at New York University,
that way.
where it's barely freezing, I believe.
Yeah, it's certainly a little bit chillier than what happens in Phoenix. So very good, very nice, awesome. And what brings you out to Phoenix?
Oh, I'm spending a couple of months at ASU.
Oh, very cool. Okay,
Yeah,
so that's
terrific.
currently my home institution.
Yeah, somehow we failed to intersect, which is a real shame.
We'll talk about that. Very good. But you're here. Very nice. Very nice. Let's see. Glennis, what do you like to do for research?
Oh gosh, all over the place. Sort of
Good.
follow my nose as interesting things come up. I've actually started life as a particle theorist and
Uh-huh.
worked on hadronic physics and
Yep.
supersymmetry and things like that. But I kind of migrated into astrophysics, actually pulled in part by cosmology. The baryon asymmetry of the universe is the problem I'd most like to explain.
Right.
And then my second most favorite problem would be the dark matter, what dark matter is.
Mhm.
And I sort of fell into thinking about ultra high energy cosmic rays quite accidentally because some 20, 25 years ago, there was a discrepancy between two different experiments,
Yes.
which looked like they required, I mean, sorry, two different experiments observed a similar discrepancy, which caused which would have required new physics to explain if it had not gone away because of experimental errors. Anyhow, so that's when I got interested, but then you get hooked, so that sort of pulled me more and more into astrophysics because I realized that you had to understand the galactic magnetic field in order to calculate the deflections of cosmic rays, and so, or, to know what they were. And so I looked at the literature and it really seemed that it could be done better. And so then with my
Cool.
student Ronnie Jensen, we really, I think, pretty much revolutionized that subject, which
Uh-huh.
now is well and thriving. And then what else did I work on? I got interested in tidal disruption events
Yeah.
because it became
Okay.
clear that the standard sources of high energy cosmic rays had problems, and I thought
Ah,
maybe tidal disruption events. And so actually, I had a very talented master student named Stuart Van Velzen, and together we discovered the first two examples of tidal disruption events in SDSS archival data.
very
And
cool.
we it was an AppJ. We really laid out the way to identify them, and that's been the way the community has done since. It's a thriving community,
Very
but
cool.
I it's just been too much to try to stay totally engaged with that. And so, what else am I working on? I continue to work some on dark matter and placing constraints. I actually have an idea that dark matter might be a six quark hadron that hasn't been
Ooh.
discovered.
Ooh. Okay.
It's it's a very appealing picture because it doesn't require new physics and it seems to sort of naturally give the approximately right abundance. And it would not, amazingly, it would not have been discovered in the laboratory. And so that's a pretty exciting endeavor.
Very nice. Well, I
But
appreciate your range there.
yeah, it's sort of it's sort of staggering. And then various cosmic ray phenomenology. My what led me to this project was that I mean my basic approach is kind of phenomenological. I feel like at least the niche that fit in
Uh-huh.
is to really try to look at what the data is telling us in any different field. Could be the
Yes.
magnetic field of the galaxy or dark matter or whatever, and then take it from there, which is what's at the basis of what I'm going to this article that we're going to talk about today.
Cool.
But as such, I've done a bunch of different sort of phenomenological studies of different aspects of dark matter that can be constrained rather than sort of speculate. This is actually the first time I've made a proposal for what the source is.
Good. All right. Well, I hope it has the same batting average as your other first. So,
This one I think I'm more proud of than anything,
very
actually.
good. Well, good. Awesome. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Ultra high energy cosmic ray production in binary neutron star mergers. And Glennys, take us away.
Well, I will have to give a little bit of background, which I will, as to
Mm-hmm.
why the data really points to something, a very special quality about the cosmic rays that was stressed by Ehlert, Okonomou, and Unger in a 2023 paper. And it had been sort of under the radar for a while, but these particles, if you look at the data carefully,
Uh-huh.
the ratio of the energy divided by the charge is essentially constant as you go to higher and higher energy.
Hmm.
I don't have in this paper a plot of the spectrum just because it's widely known, and I was just imagining that people could look that up. But in
Sure.
any event, if you do a combined study of the spectrum and the composition and how the composition evolves with energy,
Yeah.
this quantity rigidity, which is defined to be the ratio of the energy divided by the charge,
Uh-huh.
is essentially constant as you go to higher and higher energy. That would not be surprising to anybody because basically magnetic fields, the Larmor radius of a particle is proportional to the rigidity.
Uh-huh.
And it doesn't depend independently on the energy and the charge. So magnetic confinement that during the acceleration process, the speed of the acceleration process, all those things only know about a particle's rigidity.
Yes.
So the thing that was pointed out that's remarkable and is clear in the data is that the range of rigidity is very narrow. The mean, if you consider data above 8 EeV, so
Okay.
that's ecta electron volts, so
Yes.
8 times 10 to the 18th
Uh,
EV,
yeah. High energy.
8, 8, 10 to the ninth GeV.
Mm-hmm.
Anyway, if you consider that and higher, just because if you go that at that point, it's the galactic contribution is negligible. If you go down in energy, there starts to be a galactic component, and it's harder to. It's really, let's just focus on the extragalactic component. So we start at that energy. Anyway, from there to the very highest energies that have been seen, the composition is only reasonably well measured up to around 100 EeV in
Okay.
energy.
Okay.
But through that entire range, the mean value of the rigidity stays at around
Okay.
3.5 to 4.5, 5 in that range, even though you're changing the energy threshold by a factor of 4 or 10, whatever you pick, the mean rigidity stays similar. And then crucially, the rigidity range is really narrow. At any given energy, it's like a factor of 2, plus or minus a factor of 2. Now, that's the thing that Ehlert, Economou, and Unger focused on.
Okay.
And what they pointed out is that while any given source, it will have some, it might have a broad rigidity spectrum or maybe a narrow one. It would have to have a narrow one to agree with the data. So supposing it has a narrow one, but
Okay.
no source class that they could think of and that they studied as a population would have a narrow rigidity value.
Right.
It would never sit in a narrow range. If you imagine an AGN, the brightest AGN of all that would give you the highest rigidity, well, there's going to be 10 times more that whose maximum rigidity is smaller by a factor of a few or 10 or whatever, and you have 100 times more. And so you would get, as a population, a very broad rigidity range. So
Right.
they pointed this thing out. It had, as I say, it had been there in the data for people to worry about, but somehow it was
Missed.
not until they pointed out that it really became vivid. And so I started thinking, what could possibly explain that? Because they looked at AGN and long gamma ray bursts and tidal, of course, tidal disruption events are incredibly variable from one to another.
Yeah.
And
Right.
so you would never get this narrow rigidity range.
Okay.
Anyway, all the ones they looked at several classes, couldn't satisfy this for just the qualitative reason I mentioned, but they looked into it quantitatively.
Uh-huh.
Anyhow, so then I was pondering it and pondering it, and I thought, well, the only thing you can possibly think of that might be able to accelerate them would be binary neutron star mergers.
Uh-huh.
And the reason being because at least they were so similar in their starting conditions.
Yes.
Now, you could still worry that the starting conditions weren't very similar because as the merging neutron stars, they might have different spins. The masses you might have thought would range a factor of 2. Turns out, as a parenthesis, all the known binary neutron star systems in the galaxy have equal masses within 5%, but
Yeah.
that's just a fact which other people have tried to explain. It wasn't.
Standard bomb, standard candle.
Yeah, exactly. Anyway, I never heard the expression standard bomb, but that's a good one.
People
Anyway,
people use the term for type 1A supernovae, right? A Chandrasekhar mass supernovae is a standard bomb.
well,
So
that's a good point. That's a good point. Anyhow, the let's go to the figure, I guess it's figure 1.
sure.
It just happened that as I was thinking about this problem and then exploring, what is the what is the what would a binary neutron star merger be a good candidate besides this fact that the masses are always the same? A paper by Cucci et al. Came out, and this is a plot from that paper. And what they showed was a crucial thing that in a binary neutron star merger, they did this beautiful, very, very detailed GRMHD simulation, including neutrino, all sorts of everything you could think of. And what they showed that was so important is that the magnetic field that is generated by a gravitationally driven dynamo.
Okay.
And the significance of that is that the final field is insensitive to the initial field and the initial configuration.
Right. We're gonna
So that really is it then explains at an even more precise level why every binary neutron star merger will create the same magnetic initial system, which will then expand and in this picture accelerate the cosmic rays. So that's a crucial thing, this aspect that it's a dynamo, so all the initial conditions get erased.
Yep.
Wouldn't matter if it's a magnetar or what, that's
It's
one of the original neutron stars.
right.
The other thing, and that's what this paper was about, which is just phenomenal from a theorist's point of view, is that their calculation tells you the initial conditions. And so you don't have any freedom in making predictions because the system will just expand what other people have shown that is essentially homologous expansion from the initial conditions. And so this simulation plus the assumption of homologous expansion means that as time goes along until very late times when maybe it starts to interact with its own ISM,
Okay.
which is much later than the cosmic rays are accelerated, you know exactly how the system is expanding. You know what the magnetic field is as a function of time because it's essentially moving at a constant velocity, about 1/10 the speed of light.
Mm-hmm.
And as it's expanding, the total magnetic energy is essentially unchanged because it doesn't have mechanisms that efficiently transfer energy.
Yes.
That's not an exact statement, but certainly to first approximation, it's a good statement.
Fair enough.
So as the system expands, you know that the B field drops like 1 over the size at a given time
Uh-huh.
to the, sorry, let me say that. It goes like B to the, start again. Goes, the B field is a function of overall size of the system,
Uh-huh.
goes like radius to the minus 3/2,
Yes.
since the total energy goes like B squared, and the volume is increasing like R cubed.
There you go.
At the same time, because it's homologous expansion, the correlation length just increases of the sort of characteristic size of the structures in the field, increase proportional to radius
Okay.
overall. Not radius where you are in the expansion, but the outer size of the
Right.
expansion, which is growing linearly in time.
I'm with you.
Anyhow, so that enables you, let me think if I wanted to explain. Oh, anyway, so you're as a theorist is fantastic because you know exactly what's going on.
Right.
So then in this paper, the goal of the paper was to calculate what is the shape of the spectrum, the rigidity spectrum.
Okay.
And the great news is that when you can calculate, there's no free parameters really. There's a sort of order one uncertainty.
Sure.
But and you just calculate the maximum rigidity, the cutoff rigidity, and it agrees with what's been observed.
Very cool.
Let me go back for a minute,
Yeah, sure.
and maybe it's to section 2, or
Okay.
what section is this? I forgot.
Well,
Yes, the
let's kind
section.
of
Okay, good.
section two,
Section
right?
2.
Because we're in this system, right?
Right. So what we know from cosmic ray observations is that there's, as you go, as I was saying, as you go to higher and higher energy, you get heavier and heavier particles. It's not the absolute value of the mean atomic mass at a given energy isn't known that well because it turns out there's uncertainties in the particle physics description of the shower, which we know it's not perfect. And that means that you can't discriminate between A equals 40 and A equals 45, let's say, but you can tell that it's marching up together.
Mm-hmm.
So we can't say what's the atomic mass of the highest energy cosmic rays up to now. I'm going to actually argue that it's bigger than 56, but
Transition. Mm-hmm.
that's a revolutionary proposal that follows from this. But in any case,
Okay.
the reason I'm bringing this up is that in a binary neutron star merger, people have studied our process, nucleosynthesis. Well, they've studied the nucleosynthesis. And after the explosion, initially it's so hot as the material is flowing out. So there's basically, you remember the Kiyuchi plot, there was the blue surface and the
Yes.
red cone. Well, the red part had a Poynting flux about 2 orders of magnitude bigger,
Right.
thus a higher magnetic field by about an order of magnitude, and the blue outflow region. So the jet is got an opening angle of 12 degrees in their calculation.
Okay.
This is an image of their after 500 seconds after the collapse. After 150 milliseconds after the collapse,
Right.
at a radius of 500 kilometers.
Yes.
In any case, what you see from this and other work is that the structure is that there's the jet, that's on either direction, and then there's this bulk outflow,
Right.
which originates from various mechanisms. But anyway, there's this bulk outflow, and you can kind of see it's relatively uniform.
Can you imagine that expanding? Yep.
People have always assumed that cosmic rays would be accelerated in jets. It just seems like jets are the most dramatic thing. Surely they're the place.
Yep.
But in fact, in this scenario, the data tells us they can't be primarily accelerated in the jets because we know that there's higher masses in the cosmic rays than proton and helium, but
Yes.
people who study nucleosynthesis in these systems have shown that in this jet, you only get either proton or helium or a mixture, depending actually very interestingly on the equation of state of the neutron stars, which determines how long it sits in a hypernova type. I don't mean to say hypernova, sort of an excited state before it collapses. A
Yes.
hypermassive neutron star is what I wanted to say. So
Yes.
it may collapse quickly, and in that case, it's just protons in the jet. It may hang around for a couple of seconds, in which case there can be helium in the jet too, because the amount of neutrino flux is varying over time. And that particular thing depends on the equation of state, which I think is super cool, that the cosmic ray composition may be a direct measure of the equation of state, but that's a
Okay.
little bit of an aside. Anyhow, so because it's very well established that in the jet, there's only protons and possibly helium, it means that just on empirical grounds, the acceleration of the cosmic rays, that most of the bulk of the cosmic rays has to be happening in this outflow.
Yeah.
It
Right.
happens that was absolutely great news to me because it happens that with Luca Camiso, we looked at who's an expert in PIC simulations of plasma acceleration.
Yes, he is.
I asked him, could you measure the spectral cutoff in anything anything you simulated?
Uh-huh.
His specialty and the work that he and Cerrone did has largely been focused on magnetized turbulence.
Mm-hmm.
And magnetized turbulence is, by definition, an environment where the magnetic energy density exceeds the kinetic energy density of any particles that are in the
Ah,
plasma.
okay.
So the first thing I did for this calculation was knowing the initial conditions, thanks to the Kyuchi et al. Simulation and other work that people had done on the amount of material that's being ejected. I could calculate that ratio, and indeed, it's magnetic. The outflow is a case where the magnetized turbulence applies.
Okay.
Anyway, in this separate work that Luca Camiso and I did, then joined by Marco Muzio to see how well it fit the cosmic ray data.
Okay.
Anyway, Luca measured in his simulations a cutoff. So if equation one has the functional form of the spectrum that he measured. So it's the rigidity to minus some power, approximately 2, and times the Setch cutoff. And
Mm-hmm.
that Setch cutoff is much sharper than I don't have. I should. It would have been nice had I included a picture in the appendix of this paper from the paper with Camiso and Muzio. It's this one called Camiso et al. 24.
Mm-hmm.
Anyway, the Setch cutoff is much sharper than the exponential cutoff, e
Right.
to the minus r over r cut, that's associated with diffusive shock acceleration.
Mm-hmm.
I think people need to
Yes.
do peak simulations of diffusive shock acceleration to verify it's actually exponential. This was a result that was derived analytically some
Okay.
couple of years ago, that it's exponential or softer for diffusive shock acceleration. The data is much better fit by the Setch cutoff because it's so sharp. The exponential is very hard to fit the data with an exponential
Right.
unless you hypothesize an unphysically hard spectrum like r to the 0,
Okay. Okay.
which is what's been emerging from the fits that Auger was making to the data, r to the 0, or maybe r to the minus 1, but
Mm-hmm.
never r to the minus 2. But with the Setch cutoff, and when you take into account the impact of escaping the environment, this spectrum predicted from magnetized turbulence with r to the minus roughly minus 2 and the Setch fits the data beautifully. That's one
Cool.
of the things that we showed in the paper with Luca. Anyhow, I was very pleased
Cool.
to be driven to think about the outflow instead of the jet, because I could show that the magnetized turbulence applied in the outflow, and so I could use all these results. So don't go too fast beyond equation 2,
Nope.
because in this work with Luca and Marco, this coefficient, the 310 to the minus 16th is just a unit conversion.
Yes.
And then the 0.65 is the numerical prefactor relating. It's clear that the rigidity cutoff has to be proportional to the magnetic field strength times the coherence length, just on dimensional grounds practically. And in this work with Luca's work, he did the simulations, he could measure that prefactor.
Mm-hmm.
And the actual prefactor in the expanding, this is the one place there's an order 1 uncertainty in my calculation reported in this paper, because in the expanding system, that prefactor, maybe it's 0.8 or something like that. So there's that kind of uncertainty, because the geometry is a little different than the linear geometry. But it's got to be of order 1. Anyway, in this calculation, I took that prefactor. But what I was starting to say is I was thrilled because I didn't know how to, or would have, all the analyses with acceleration in jets are basically just have a wiggle. There's no calculation that I'm aware of that has a real numerical prefactor. And so for the jet acceleration, I would have just only been able to make very rough estimations.
Order of magnitude estimate. Yep.
Yeah, something like that. So that was a bonus that I had given that I could show it was the conditions are the conditions for magnetized turbulence. There was just no wiggle room about what the acceleration should be like. It should be characterized by magnetized turbulence, so it should have the equation 1 functional form where P is 2 or 2.1, something like that.
Mm-hmm.
And I could take this equation 2 to be accurate within a little bit.
Cool. I'm with you. Mm-hmm.
Okay, so anyhow, on those grounds, I decided to focus on the turbulence. As you'll see, I was greedy, and after solving that problem, I went back and said, well, supposing I can approximately treat at large radii which it turns out, it's going to turn out that the main region of acceleration is around 10 to the 14th centimeters.
Okay.
Maybe when you're that far out, even the jet is starting to be describable by magnetized turbulence, and as opposed to specifically a few big shocks. And then I can do further calculations for the light component, possible light component of proton or helium in the jets.
I'm with you.
Okay, so with that explanation for why we're talking about the magnetized turbulence, and the explanation of why we know the initial conditions, because that's what Kyuchi et al. Give us. They also give us the coherence length. You can just look at the picture and you see that the coherence length, I forget the prefactor, but it's like, it's a rough, I could look it up. Anyway, you can see it's about equal to the radius or the radius.
Okay, let's see. Go ahead, keep going. I'm with you.
Anyway.
We'll find it.
So I know all of the numbers I need, and then
R over 3. Mm-hmm.
Okay, very good.
Mm-hmm. Okay. Okay.
So now we have this expanding medium, and the question becomes, where is the acceleration going to occur?
Okay.
So initially, the field strength is really high, 10 to the 13th Gauss, at 500 kilometers, or actually 310 to the 13th. And as it expands, it's dropping like r to the minus 3 halves.
Yes.
So, but the coherence length is growing like r.
Yes.
So the maximum rigidity, which is going to be proportional to the field strength times the coherence length,
Uh-huh.
will be decreasing with R. It'll be going like R to the minus one half.
We move inward. Yes.
But so you might have naively said, "Oh, well, it'll accelerate right at the right near the
Cross point.
as soon as the nuclei are produced, it'll start accelerating." But that's not right, because if the nuclei were to get so energetic so early, then synchrotron radiation would cause them to lose energy and come back down. So let's go to that plot in, or the equations anyway, in the first appendix.
Okay, so let's slide down to Appendix A. There's two awesome appendices here, people. Check them out. And
Okay, that's
first
it. Oh, there's that
appendix,
picture, we just passed it.
yeah. Synchrotron cooling cutoff rigidity is what we're covering here. And the first two equations, well, let's get the first one here.
Oh, right. So the acceleration time is just proportional to the coherence length divided by c. That was another thing we measured in this paper with Luca Comiso,
Okay, that's simple,
which
straightforward.
is also, by the way, an AppJ letter.
Yay.
It's good for AppJ. So let's go up and look at the plot and the equation 2. So let's look at figure A1 and equation A2.
Okay, let's put those together.
Okay.
There we go.
So basically, the story is going to be that when you've expanded enough, so initially the synchrotron loss time is very much faster than the acceleration time.
Yeah.
But as it expands, so the particles don't reach their maximum acceleration by any means. But what happens is that they just gradually increase their rigidity. And what you can see in equation A2, most astrophysicists have this expression memorized, but I've rewritten it in terms of charge and mass and magnetic field, because so the prefactor is just a number. The usual expression that people may remember, I've just rewritten this way. Gamma is
relativistic factor.
That's right, and it's essentially becomes a constant. It's this, well, this is a convenient way to write it. I could rewrite it in terms of energy. So what I've plotted in figure A1 is asking what is the ratio of the acceleration time, which was in equation A1, divided by the synchrotron loss time. When this number is less than 1,
right,
you're in good, it's good for doing your acceleration. You'll never accelerate into an energy where this number gets bigger than 1.
right. Okay.
So what this is plotting is at a particular rigidity, namely the rigidity around 5 PeV, which is what we observe is the maximum. I'm plotting the ratio for different nuclei.
Okay.
And helium is even below, it would cross unity at a factor of 3,700 Gauss. But what this tells you is if you're trying to accelerate oxygen, the maximum field that you can get where it will actually accelerate it to higher energies is something like 900 Gauss. Or if you're accelerating heavier stuff like iron or protons or silicon, it's around 400 Gauss. And so this helps you, with this, keeping this in mind, helps your intuition that you expect that the region of acceleration is going to be at quite large radii where it's expanded enough that B isn't too big. Of course, you pay the price and the total maximum rigidity because B times the Larmor radius is decreasing, as we said. Okay. Now let's go back to, I'm guessing it might be figure 2.
Yep. Okay, good. I'm with you. Thank you for that appendix and figure 2. Right, we're on our composition.
Yeah, there it is on the left side of this page. Yes. Okay. So what this plot does is combine all of the above information as a function of radius it's showing the cutoff rigidity. The black dotted line is the maximum you can get from the acceleration mechanism for the different nuclei. And the colored lines are the maximum that's allowed by the synchrotron emission
Right.
condition. Therefore, for the different nuclei, the maximum, the cutoff energy that they can achieve in this system is read off from where the colored lines intersect.
Right.
In the outflow, so we're going to have to come back to what governs the relative composition. That'll be the next thing to talk about.
Cool.
The relative amounts of the different nuclei.
Yes.
The people who simulate our process nucleosynthesis, or simulate nucleosynthesis in the binary neutron star mergers, as I said, they find that in the jet it's exclusively proton or helium, so we'll leave that's secondary. That's going to be a secondary component.
Right.
In the rest of the outflow, it's initially very heavy, something with A above 40. And out to really high A, where you have our process nucleosynthesis. And so later we'll come back to the processing the nuclei go through before they get out. So that's something that'll have to be calculated in the future. But the colored lines here, oxygen through tellurium, would be the typical cosmic rays that are primaries in this system. And so you see, we can read off, it's written a little bit further. We see that they're indeed all accelerated at they get their maximum rigidity at roughly the same place.
Right.
But it's quite interesting. You don't get a perfect so-called Peter cycle. People usually, when they're fitting data, assume that all of them that all that matters is their rigidity. But what we see is that that's not quite true in this system. It's within the uncertainty in the data, I don't think certainly right now you couldn't tell. But maybe in the next generation of cosmic ray experiments you could. Can you scroll down a little bit? I think the values of the rigidity are shown in the caption, maybe.
Let's
The
see.
bottom of the caption. Oh, no, right. It happens to be the first line.
First line.
So that's the radius for different nuclei. And then I guess it's on the previous page at the bottom where it gives the list of values of the cutoff rigidity. And so if you set aside, if you don't pay attention to proton and helium, which are dominant above in the energies above 8 EeV, where the data is really good, that's already higher than where you have very much helium. So the cases that are well constrained in the measurements and are contributing are the higher energy ones, say somewhere, or the higher mass ones, say between oxygen and higher. So you see that the rigidities for them are 7, 6.4, 6, 5.9. And then if you go down a little bit lower, you'll see what the fit to the data gives is the cutoff in the data is 6 plus or minus 0.8, 0.9 or so. And in the fit that Camiso and Muzio, well, in this case, it was really Muzio who did the fit, but in our paper, it's 6.3. So you see, it's from a theorist's point of view, it's sort of
it works. It works.
And it's really with no free parameters. It's got this sort of maybe 20%, 50% uncertainty because of the prefect.
But not factors of 10 or 2 even.
Yeah, exactly. So that I think is the first thing in favor of binary neutron star merger scenario is the fact that it's an explanation for this source to source being identical sources. And then the second thing going for it now is that you have an explanation for the actual value of the cutoff in the spectrum.
Nice. Very nice.
Okay. So maybe if we're following the development in the paper, we can just then say, well, supposing we ask ourselves, what about the stuff in the jet?
Right.
There's only proton and or helium.
Right. Go to disintegrate.
And so let's go to the next plot, figure 3.
Right. So this
It's
is for the
like figure 2.
outflow, and
It's
this
the
one's
same,
for the jet.
right, the same, exactly. And so I can do the same thing and say, well, supposing at large radii, I can use these expressions for magnetized turbulence. Really, any model will always have
Okay.
that same functional form, and it'll just be a question of what's the coefficient. But anyway, if I use the coefficient and I take the coherence length from the Kiyuchi simulation, then I get this prediction for the cutoff rigidities. And the radii, you see, this is happening at another factor of 10 larger radius, just because the B field is stronger by a factor of 100, so you have to go out to higher radius to let that drop.
Uh-huh.
And then the
Okay. Yeah.
just a little bit below, it tells yeah, let's go a little down further, you see that maybe it's, well, the maximum energy for protons, and this would be 10 to 15 EeV,
Okay.
and, oh no, sorry, that was another
There it
fit.
is.
I guess it's on the previous page where the numbers are. But here it is, right, that the protons and helium would have arc cut of 11 and 17.
Ah, there we
So, but it corresponds to, that would mean that you'd have 35, if you have helium, it would reach 30, its cutoff would be at 35 EeV. That would be quite a bit higher than any of the others in, and whereas for protons, you would get this secondary higher energy component at around 11. The,
Right. Okay. Yes.
that and at this point, I can't predict the relative amount in the two. But one thing that's fascinating is there was a study
Yeah.
actually led by Museo a few years back. I don't remember the year, but it's in here.
2019.
Where, yes, where there's always been a little bit of a hint of a light component in the highest energy cosmic rays. And of course, that would be very welcome to the experimental or to the cosmic ray community, because then the amount that they would be deflected would not be so problematic. Right now, you can't point to the sources because you go up higher in energy, but you don't change the Larmor radius because the charge goes up too.
Right.
And so the problem of correcting for magnetic deflections, especially in the galactic magnetic field, doesn't get better. So the possibility of a subdominant light component has always been very appealing. Anyway, Museo et al. Did a study in which they fit, allowing for there to be a secondary light component and a pure proton, and they found it improved the fit a lot. The data has now gotten much better on the composition, so I think it should be, I hope Auger will redo that study.
Cross fingers.
Yeah, I'm sure they will.
Go, yeah.
All
Okay.
right. So if I just progress through this at lightning speed, I should pause and ask if you want to ask questions.
No, I'm perfectly good. I'm following you well.
You're you're representing the audience. The in section 8, I looked into what's the total. What do we know about cosmic ray? Hang on a second, I have to interrupt.
All good?
I'm doing this seminar online. Okay, so in this section, I talked about, hang on, could you just come back later? Thank you.
All good?
In this section, I talk about, well, one thing that's a fun thing to do is to say how much mass is there that gets
Swept up.
You're right, we start with 2 solar masses roughly of material. How much of that mass becomes ultra energy cosmic rays?
Mm-hmm.
So I can do that calculation approximately if I know the total energy in cosmic rays produced per event. It's, there's some uncertainty of what that is. And I can then just divide by the energy per cosmic ray in the spectrum.
Mm-hmm.
And it's interesting. The answer is roughly a billionth of the mass gets, um,
It's all rated.
yes.
Mm-hmm. Mm-hmm. Okay. Good. I'm with you.
Well, I should say it's not a billionth of the total mass because a lot of
Billionth
that
of the solar.
collapses into the black hole. But of the material that escapes collapse into the black hole, it's around a billionth.
Mm-hmm.
Anyway, I think that's nice for intuition about what fraction of the nuclei are getting picked up into this acceleration.
And then you multiply by the total, and yeah, you'll get
Right.
right.
That's a very, very, very rough,
Approximate.
just to
Yeah.
just to give one an idea. Anyhow, the next
So it's
part
good to get the
is,
scale.
I would say, in this scenario, the aspect that is, how to say, a potential issue, but right now it's not, is are there enough binary neutron star mergers
Ah,
to account for the the observed amount of energy in ultra energy cosmic rays?
right.
Because an accelerator, a system, injects a certain amount, and then it loses energy through GZK energy losses and so
Mm-hmm.
on.
Yes.
And then all of those different sources that we see out to, when I say loses energy, I should emphasize that these are mostly nuclei, and mostly they just lose nucleons. And so there are A changes, and they lose energy not because the energy per particle is changing, but they're just losing particles.
Right.
To some extent, they also lose energy by like beta Heitler, which actually reduces the energy per particle.
Uh-huh.
In any case, we don't know well the energy. There's two pieces of that we don't know well. We don't know how efficient the system is for accelerating, what fraction of the binary neutron star energy release goes into ultra energy cosmic rays.
Okay. Mm-hmm.
And then the other thing is we don't know the rate of binary neutron star mergers.
Getting better, but yeah.
Yeah, that's right. It's and right, there's two ways that we can measure the rate. One is from short gamma ray bursts.
Okay.
There's many short gamma ray bursts that have been observed, but it's not well known, or it's uncertain to some level what the efficiency for seeing a short gamma, for seeing a merger and seeing the jet essentially from the short gamma ray burst.
Mm-hmm.
In any event, those two communities have now estimates of the rate. This equation 3. So equation 3 is an expression for the energy in ultra energy cosmic rays per merger if it's equipartition,
Okay.
and where F EQ and F jet are the fraction of the, well, if it was equipartition, those would be a half.
Okay. Yeah.
But it's interestingly,
Energy.
actually, in the simulations that Luca did
Yeah.
in that static case,
Uh-huh.
it was a half.
Okay.
In the expanding
Yeah.
case, we'll get to later things that need to be done. In the expanding case, it would be very important to understand to what extent the energy in the magnetic field is efficiently transferred at the last stages into the ultra energy cosmic rays. Like I say, in the static case that Luca simulated, it was in the end, the magnetic field energy drops off so that it is equipartition. And if it were equipartition, then the energy can be quite big in cosmic rays.
Cool.
So in equation 4, this is a sort of standard estimate of the energy injection rate that you need.
Aha. Okay. Yes.
This is now
Yes.
averaged over time.
Hmm.
And so if we know the merger rate from those two equations, we can ask under what. And by the way, if this is really, as one might hope, the sole source of ultra-energy cosmic rays, or like 90% of them, which this study of Ehlert, Okonomou, and Unger would support, you should be able to predict the rate of cosmic rays. It's not
Right.
just that you
Right.
need to have enough.
Right.
In any event, that's not yet possible. But if you use, and this number 10 to 1700 is now updated, and it's more like, it certainly doesn't go up to 1700. I forget what the number is now, but it's more like
Mm,
200 to, if you combine the two,
get off the top of my head.
both the SGRBs and you see the short gamma ray burst estimate is roughly
That's,
1800 per cubic gigaparsec per year, but with big error bars. And
huge.
anyway, if you'd use the lower bound from
Yeah.
the short gamma ray burst and the upper bound, you would say this rate gamma 3, which is what essentially it's the efficiency of converting cosmic ray energy, needs
Okay.
to be in this range 0.3 to 1.7, and with where 1 is kind of the canonical value. So
Right.
right now, the energy injection rate looks just fine, but for example, if the binary neutron star merger rate were shown to be much smaller than the short gamma ray burst,
Yes.
if the LIGO Virgo Kagra number were to come down where it was actually in conflict with a short gamma ray burst rate,
Yes.
which could happen if it turns out the short gamma ray burst people didn't properly estimate their efficiency for seeing them or something, then
Overestimate.
that could happen. Then could be a
Sure.
problem for this scenario. But right now it looks just fine.
Okay. Okay. Keep an eye out for that. I'm sure we'll talk about that in the future here in a bit. Okay.
So let's see what else is in this paper. Oh, so
Other
one of the
signature.
most wonderful things is that it's very predictive.
That's always a good thing.
One of them, the most striking prediction,
Mm,
is that the the gamma ray, sorry, the neutron star mergers are the source of ultra-energy cosmic rays. We can't make a correlation. We can't do multi-messenger correlations between the ultra-energy cosmic rays and the binary and the merger because the time delay is incredible. Even though the extragalactic deflections are small, the distances are immense, and so you have time delays. I may have put a number in here, but like it could be 100,000 year time delay.
about a mega year.
Well, that's the arrival time, but the time delay. In any event, right? This is for canonical distances and a distance of 1 megaparsec. It would be, but for a distance of 100 megaparsecs, let's say, oh, hey, good for you, you did it perfectly.
Okay.
Around it. Anyway, the time delays are so substantial you don't see it. However, sometimes the ultra-energy cosmic ray in its environment will interact with a photon in the environment. And then it produces either it produces a pion or it spalates a nucleon.
Yeah.
And if it spalates a nucleon, which is a more common situation, the energy so that if it's a neutron, it'll beta decay.
Yes.
So there's two types of neutrinos that get produced in this after the cosmic rays are created, while they're still in the environment and there's a more intense photon field.
Okay.
One of them are neutrinos coming from neutrons beta decay, and they would have an energy of a couple of PeV.
Okay.
There's of order 5 events that have been observed with energies in that range of
Yes.
neutrinos.
Yes.
And then if it came from a pion production, those neutrinos would have an energy like the KM3 net neutrino. So
Okay.
conceivably, the
Okay.
KM3 net neutrino came from that source.
Okay.
I mean, I think that would be its explanation. It's perfectly correct energy range.
Mm-hmm.
The only thing that's funny about that is the consistency. I guess, assuming there's no problem with that actually being a neutrino, then Ice Cube was just unlucky because they were both looking in the same direction.
Drat. Okay.
Anyhow, um,
Mm-hmm.
well, it's a sort of factor of 10 higher exposure, so people are unlucky at that level regularly, or lucky at that level.
Mm-hmm.
Okay, so in any event, if you find a neutrino above a PeV,
Yes.
it pretty much has to have an ultra energy cosmic ray origin. And if all ultra high energy cosmic rays were
Okay.
produced in neutron star mergers,
Mm-hmm.
then every neutrino will have a simultaneous gravitational wave coming from the same direction
Uh-huh. Mm-hmm.
within
Cool.
some amount of time. And so in this section, I calculated, well, basically, I know that it's around 10 to the 14 centimeters where the cosmic rays are produced.
Mm-hmm.
And it takes about a day for the system to expand that far.
Mm-hmm.
And so the time delay between the gravitational wave and the production of neutrinos would be of order a day.
Okay.
So
That's a nice prediction.
that's
Mm-hmm.
and the prediction would be that every neutrino will be accompanied by a gravitational wave, and
Uh-huh.
then the question becomes, what's the sensitivity to be able to pick it up? And I did a very rough estimate in an earlier paper in a PhysRev letter, where I first laid out the scenario, and I thought maybe with the next generation Cosmic Explorer and upgraded Ice Cube Gen 2
Uh-huh.
that you would get roughly one coincidence a year, but that has to be calculated better. And thanks to this being so predictive, the Kiuchi et al. Group is going to give me a model of their calculation for the photon field, and
Huh.
then I can calculate the absolute rate.
Yeah. Okay. Nice. Very good.
So that's one prediction. And the other prediction, which actually there's evidence for it, but it's not yet proven, is that there can be a component of cosmic rays at higher energy, because in this scenario, some of the uh, nuclei that start off as
Yep.
our process elements won't have been broken up.
Yep.
And so you'll have some small contribution that starts off as like with a Z of maybe 50, like in the
Yeah.
R process peak of xenon and tellurium.
Okay.
And so if it starts off at that energy, it'll lose some nucleons as it travels to us, depending on how far the source is.
Mm-hmm.
But then you would expect a small level of high energy events. And indeed, we do have two events above 200 eV, nominally around 240 eV.
Mm-hmm.
And whereas the mean rigidity is around 4.5, as I was telling you, it's observed not to change in the region where it can be well measured.
Right.
And when you back that out and say, what Z does that correspond to for these highest energy events, it's Z of around 50.
Yes.
So that's terrific. That's a strong hint. The reason that's not yet, I would say that's not firmly established, has to do with this thing I mentioned earlier, that due to imperfections in the modeling of hadron interactions at extreme energies,
Mm-hmm.
which impact the shower development.
Right.
Um, and there's different models of for this that are, available, and none of them fit well. But they typically have like a range of 10 or 20% uncertainty in, or not, or just discrepancies between what mass they would assign for a given energy.
Okay.
And so until that's clearer, well, it's possible that there's sufficient data already, and I'm hoping Auger will look at this because they have of order 10 events above, more than 2 sigma above where iron should be.
Okay.
But it has to be seen. It would be very interesting if it's possible that the Auger data could already be
Already have it.
used
Yeah.
to demonstrate that those are heavier. If they're heavier than iron, that's really extremely strong evidence for this, because there's essentially nothing but iron in all of the normal environments that people have studied, like
Mm-hmm.
tidal disruption events or AGN or long gamma ray bursts.
All right. Okay, cool. I'm with you.
Okay, well, I think that covers the 9.2 is a rather esoteric, 9.3 is sort of an
Okay.
esoteric thing, so I don't think we should
Okay.
necessarily go into that.
Okay, and we're
The
gonna
fact that those rigidities of the cutoffs aren't identical is in principle a test,
another test. Mm-hmm.
but they're so close that I don't think this generation, there's no hope in this generation of cosmic ray
Okay.
experiments.
Pretty small. Yeah. Okay. Gotcha. Okay, cool. We're going to hang off on section 10 here for a bit. So, Glennis, I want to thank you so much for walking us through your very awesome predictive article. Thanks. Let's see. And you hinted at it several times as we went along. And so let me ask, where do you think we go from here, given the published article? So what are some happy next steps that could help verify this model or refute this model, and where we go?
Well, certainly looking closely at the composition of the highest energy events to
Okay.
find out if they're actually consistent with iron.
Okay.
If they're not, and they need a higher mass, that would be a very strong evidence.
Okay.
The things theoretically I think one wants to do is explain the composition that is observed. And so we know the initial conditions. They're all this out, well, pretty well. And the people who do our process nucleosynthesis, maybe they disagree with each other at the factor of 2 level. But the initial conditions of what's the spectrum of masses is quite clear.
Mm-hmm.
And I believe it's pretty clear what calculation has to be done. Namely, as this flow is expanding, initially everything is extremely cold, but some fraction of these heavy particles will get picked up by in this turbulent environment
Uh-huh.
and get enough energy. It turns out it's around 100 MeV. It's still quite a low energy,
Okay.
and that's sufficient to fragment the nuclei when they hit each other.
Ball. Mm-hmm.
And I've done estimates of, and how that would go, and it remains very dense initially, right? This is extremely dense initially. It's expanding, so the cross section for these things is high enough.
Okay.
And I think that and therefore so a nuclear physics problem would be to make a reaction network that follows how the composition evolves of the high energy event, of the energetic events. And then you would be able, in principle, you should just be able to make a first principles calculation of the composition that's being accelerated.
Okay. Okay.
So that's an exciting prospect. The other thing that, in terms of really important work, which I hope people will pick up on, and this is for the plasma physics community, I would say, the people who do PIC simulations should
Yes.
look
Right.
at whether this prediction of the spectrum being exponentially cut off and diffusive shock acceleration, they should measure that like Camiso and did for the magnetized turbulence. Because I would say if the prediction, if it holds up, this theoretical analysis that showed an exponential cutoff or softer, if that holds up, those models are simply excluded by the data.
Okay, good.
People should really pay attention to the cutoff form. So PIC simulation people should study that. Another thing that nobody seems to pay attention to, but is crucial for this, is what's the efficiency with which particles in this cold plasma will get picked up in the turbulent medium and then
Okay.
and start to join this high energy thing. My picture I have, but it's not based on simulations, it's more intuition, is that the whole system will, you'll pick up low energy particles when it's fairly dense, and you'll so to speak populate the part of the spectrum that's semi-relativistic and capable of being accelerated to highest energies. You'll populate that early on, and then as the system expands, that whole system will just move up in energy,
Okay.
regulated by the synchrotron emission.
Okay.
And
Definitely.
so
Yes.
actually finding out how that works and what is it that governs this pickup process, that'll be critical to predicting what's the actual absolute production of ultra-energy cosmic rays. So, and that's, I think, well within the capabilities of the plasma physics community.
Okay.
It's not a trivial project, but it's definitely, I
Doable.
would think no reason it can't be done pretty soon.
Very cool.
And then in that a similar vein, well, you have to also calculate in more detail the process of escape after they're accelerated. Well, how efficient is the highest energy ones just get out, but the ones that are lower energy are somehow trapped in this magnetized turbulence, and they may wind up losing energy instead of getting out.
Right.
And so
Sure. Okay. Hmm.
I guess that's the main work. That's quite
Cool.
a bit.
Well, that's quite a palette of things for people to go after. So, uh,
Yeah, I think
yeah,
so.
it'll be really cool to see what happens over the next couple of years as people go after various aspects of this and to either verify or otherwise parts of this intriguing model that you have. So,
Thank
very
you.
nice, very cool, good. Glennis, thank you so much for
It's
talking to
been a
us about
pleasure
your.
talking to you, Frank.
Sure, thank you.
Everybody should feel free to contact me if they
Oh,
want
there we
to
go.
want some.
And glass is not hard to find. Neither am I. So, so very good.
Very
All
good.
right. That will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye.